Welcome to session 6 of the training. Before we get into the main topic, which is pond design in this session, I want to introduce the concept of phase management. So the starting point for this session is either the end of exercise 5 if you carried on working from that, or open the exercise 5 IDDX file from the answers directory, or you can just import the MicroDrainage file that we used in the previous session, in fact in session 4, and start working from that. So any of those are an acceptable starting point. Then the first thing we're going to do is do a file and save as, and we're going to save this in the save work here directory, and we're going to call it exercise 6. Okay, and save that. Now, as I said, the first thing I want to do is to look at this phase management. Now, what this is that InfoDrainage has the possibility of saving a number of different models or designs within the same IDDX file. So one file, lots of different designs, or alternatively sometimes called phases, or possibly called scenarios. So one example could be that you're looking to design a solution to a flooding problem. There may be a variety of potential solutions to that. Build a pumping station, store some of the flow, put an extra pipe in, and you may want to investigate all of those multiple options. So often, as we're going to do in this case, you're going to have one starting model, and from that we're going to build a number of scenarios from it. And the way it works is that if you find the phase management within the tree view, if you just open that, you'll see there's often a storm, possibly a foul if you're working on foul networks as well, listed there. And then underneath that, currently there is just one phase. It's called surface network 1 in my example. It may just be called phase or phase 1 in the example that you're working on. But basically there's going to be a light bulb, a go, and the name of the network that we're currently working on. So what I'd like you to do is right click on the name, and we're going to duplicate that phase, and then right click on the one that's just been created and rename that, and we're going to call that pond design. So at the moment we've now got two networks, and you have to be very careful to know which one you're currently working on, and you switch between them using this drop down. So we can either work on the surface network or on the pond design. So if we make any edits, anything at all, adding, deleting, changing things, then it would be done to the pond design one in my example. The light bulb indicates simply whether you can see the network or not. So I'm going to switch it off for the surface network, the one that I'm not working on. And the go is when we come to run some analysis, hit go, it can analyze multiple networks in one go. So it would run all the 18 storms that we were looking at previously on both networks. And in many cases, you don't really want to analyze multiple networks. So often you would switch off, it's just set to stop the network that you're not working on. So we can't see it and it's not going to be analyzed, but it is still there in the background. Okay, next thing I want to do is I want to return to a topic that I introduced previously, and that is the issue of contributions to our network. And you remember from a previous session I talked about the fact that in a typical suburban design catchment we're going to have a pipe or series of pipes perhaps. So we've got a pipe there, so the flow direction is going to be like this. Then what we're going to do is, this is going to be our typical designed catchment. So we may have a series of houses here. We may have school or larger buildings here. Something else here perhaps. We may have also the roads. So there'd be some roads like that. And I've talked previously about the fact that our main job during the model build phase is to stipulate that we think that this area, and it's our skill and judgment as design engineers to say we think this area drains to this manhole. Okay, and what we also have to do, either by using GIS or estimating, we have to work out the PIMP value, percentage impermeable. In other words, the amount of catchment that has been tarmacked or concreted over, because crucially, InfoDrainage only accounts for runoff from those impermeable areas. So we're only going to get runoff from the roads and the roofs and nothing from all the other areas, the back gardens, the grass verges, everything like that. So the first thing we have to do, and we have covered this in previous exercises, is if you go to the build and then tables, look at the inflows, the crucial parameter to look for in this case is the percentage impervious. We talked before about if you were designing a runway for an airport or a large warehouse or something like that, then it might be 100% impermeable. But a typical suburban environment would be maybe 60 or 70% impermeable. So crucially, for the vast majority of the models that you work on, you're going to be looking at this column here and either making a global assumption or more accurately making an individual assumption for each catchment, or better still to do some sort of analysis using GIS or similar to measure the amount of area within those polygons, convert that into a percentage impermeable. So in this case I'm going to assume just this blanket assumption that everything is 60% impermeable. However, that is only part of the story. Coming back to this, we've now said we're only going to get a contribution from these buildings or these roads into our manhole that we're currently designing the pipes for. However, the second part of this is how much runoff do we get from those roads and roofed areas. Now, there are some more sophisticated ways of calculating this value, particularly in our InfoWorks ICM product that has a variety of different runoff models, the new PR equation, the Wallingford PR equation, and others, SCS, those sort of runoff models, which use factors such as how wet the ground is, the soil type, parameters like that to calculate a percentage runoff. However, InfoDrainage and MicroDrainage just make a very, very simple assumption that there is just a fixed percentage runoff from these roads and these roofs. The default is during the summer, when the ground is assumed to be a bit drier, is around 75%, 0.75 here, and during the winter it's 0.84, 84%. So we're saying that of the rainfall from a winter storm that lands on the roads and the roofs, 84% of it makes it to the manhole, 16% along with everything from the permeable areas, none of that makes it to the manhole. Now, some people dispute that assumption. They say that these numbers should be increased, and in certain situations they should. If you want further advice on these numbers, then that's available from the support team, but these are crucial. This really influences how much rainfall gets into our sewers, and therefore the size of the pipes themselves, the size of the storage, and everything like that. So you really need to take a view on what these values should be. Okay, so we've now changed those values, and we're going to look at the pond design. So do I want to keep the changes? Yep, as I close that. Table. Okay, so this is what we're doing in this exercise. Just got a quick bit of PowerPoint here. So we looked at this slide in previous sessions as well. So our basic task is to firstly design the pipes, and we've talked about the two-stage design process in previous exercises. Then what we do is we have to do an analysis of the receiving watercourse, or often it will be dictated to us what we're allowed to discharge into that receiving watercourse, and we did that calculation in exercise 5. So you'll end up with a flow rate that you're allowed to discharge from the site. Now what we're doing in this exercise, in exercise 6, is we're going to design a discharge control to meet that limit of discharge. So it may be an orifice or a pump or a hydro brake, but something is going to have to limit the flows coming through the pipes so that we don't exceed our limit of discharge into the receiving watercourse. Now you can imagine once we've concreted and tarmacked over our catchment, we are going to get more runoff from it, and that runoff is going to be faster. So it's going to arrive at our discharge point much more quickly than it did before. So the traditional solution to that is to build a storage or attenuation structure just upstream of the outfall, store the water there, and release it slowly into the receiving watercourse such that we don't exceed the limit of discharge. And that's the exercise that we're going to look at right now. Then later, there are now more sophisticated methods of achieving this limit of discharge and protecting downstream areas, and that would be to build SuDS, alternatively called BMPs or LID structures, around the catchment to achieve the same goal, to work basically in harmony with the environment, infiltrate some of the water rather than discharging it. And we're going to look at that in subsequent exercises, but now we're going to start with perhaps the simplest design solution, which is just to build a big tank or pond immediately upstream of the outfall. This is the pond that we're going to build. It's going to have a base level 30.434, a top water level of 32.109. It's going to have a 1 in 4 side slope. It's not drawn to scale here. The reason we're going for a 1 in 4 side slope is not because of any hydraulic constraint. It's just considered that if somebody fell in the pond, if the side slope is 1 in 4 or more shallow than that, then they would have a decent chance of crawling out again. So it's purely from a safety concern rather than a hydraulic analysis concern. Okay, so I'll just close this a second. Okay, so I want to look first at where those parameters came from. So what we're going to do is, if we zoom in, this is where the pond's going to sit down here. And if you double click on pipe 1016, it will bring up its attributes. So the upstream cover level of that is 32.309. Now I've assumed a 200 millimeter freeboard. In other words, I don't want the water getting to within 200 millimeters of the cover level at that point. Hence, the top water level in this case is going to be 32.109 meters. Now the base level is taken from the upstream invert level of that pipe. So we can see the upstream invert level of that pipe is 30.434. So we can't put the pond any lower than that because we need the water to flow out of there. Okay, so that's where the top and bottom of the pond come from. And as well, we know the side slope. If you've completed exercise 5, you'll know that we arrived at a Q-bar value in this case, this very UK design-centric design criteria. However, wherever it came from, there's going to be some limit of discharge. And in this exercise, we're going to use a limit of discharge of 16.1 litres a second. So we know pretty much everything about this pond now. We know its top water level, we know its base level, we know its side slope, we know its limit of discharge. The one big thing that we don't know is simply how big it should be, and that's what we're going to do now, is design that. Okay, so I'm going to cancel out of here. I'm also going to bring in my surface data. You may already have it loaded. If you don't, we're going to load it in again now. So right click and load surface. Brings us back to this form that you'll be familiar with if you've done the previous exercises. We're going to load it in from our InfoDrainage specific format. So whether you load it in from the Save Work Here directory or from the Answers directory, load in that imported surface and press OK to that. It's useful to have it in the background. You'll get a message. We've brought in this surface. Do we want to update the cover levels of the manholes based on this? I'm going to say no at the moment. I'm going to keep my existing levels. So we've now got this surface. I don't actually need it to see it at the moment, so I'm going to switch it off, but it is there in the background. Okay, so I've got some data loaded in, I've changed some things, good opportunity to save the model. Okay, so let's go and design our pond now. So it's going to be down here near the outfall. What's actually going to happen is I'm going to delete pipe 1015. So just highlight it using the select tool, press delete on your keypad, and it should disappear. So rather than the water flowing through a pipe from one location to the other, it's going to now go through the pond. Now I could just start to digitize the boundary of the pond from here, but first I'm going to bring in some CAD data purely so that we all create the pond in the same place. So from the tree view, right click on the CAD data and import data. Select the file that we're going to import. It's going to be in the data directory, and it's the file called pond outline. So we're not taking any information from this other than its location. So it's not as if we're importing it as we were in previous exercises to provide some of the data, purely a picture. So we've got the picture there. It's in one of these layers, I must admit. I can't remember which one, but we could switch off most of them and find it if necessary. But we'll just import it there. So that is going to be the starting point for the outline of our pond. Okay, now in the plan view, I need to make sure that the snap tool is switched on. And the next thing we're going to do is over here from the toolbox, if you expand the stormwater controls, you'll see that we have a variety of different stormwater controls that we can create. And we're going to be talking about several of these as we come to look at SuDS later on. But for now, we're just going to take the pond, left click, drag it. By convention, we put it somewhere within the center of the polygon. You'll see that the icon changes. I'm just rotating the wheel to move in a bit. And we can start anywhere and go in any direction, but click on the 8 points to digitize the pond. And then right click to finish. And it's created the pond. Let's not worry about this dotted line, I'll explain that later, but basically it's looking at the furthest distance between 2 points, which is actually irrelevant for a pond, but for other substructures it does have some relevance, and we'll be explaining that when we get to the SuDS features. Okay, remember the good practice that once you've created something, it's always good to then immediately select the select tool such that we don't then create a series of ponds by accident. Okay, and if we now double click on the pond, we bring up its attributes. You remember from the diagram earlier, I talked about the fact that we had a top to this, so the exceedance level, the top water level, is going to be at 31.109 meters. And if you click on depth, it allows you to then type in a value for the base, which is going to be 30.434 meters. Actually, I've done this wrong. You need to type in the top water level, which is 31.309, and then we're going to put in a freeboard of 200 millimeters to give us a top water level of 31.109. There is the possibility of putting in initial depth if we want the pond to be partly full at the start of the simulation. In our case we don't. It's going to start from dry. It's only going to be used when there's flow through these pipes. So we're going to start from 0. Now the next thing is we need to define some initial characteristics of this pond. And what we have is this depth area relationship, which leads to a volume. So the way it works sort of conceptually, what we're going to be trying to do is so we define an area at a particular level. So at the first level we define an area, and then we might define an area at a higher level and a further area at a higher level. Once again, I can only apologize for my drawing skills. And then the software will link them all together, and from that you will get a volume of storage. So that's why we're defining a depth against area relationship, is that once you know the depths and the areas, it builds into a potentially quite a complex structural shape. However, our initial guess is to say that, so the difference between 31.309 and 30.434 is 1.875 meters. So the way you do it is we're just going to have a vertically sided structure to start off with, and then whatever that area is there, you can copy it, I think. Yeah, so you can copy it there, and that gives us a volume. Sorry, I've still got that wrong. It should be 32.309, or 31.309. Okay, so 32.309 minus 30.434 gives us the 1.875 meter depth on the pond. Okay, so at the moment we've got this shape extending down vertically from the cover level down to what we hope is the invert level of this pipe. That's the intention. Now the first thing we do is to start to put this side slope in. So go into the sizing calculator, and the method is going to be a side slope. The side slope we're going to use is 1 in 4, and as I said, that was purely for safety reasons. So at this stage, what it's going to do is, we've got this, I'm going to draw this in plan view now. So we've got this area that we've just digitized, and the question that we're asking is that the base of the pond, like that, extending from there, or is that the top of the pond, so we then bring it in like that? What does this area represent? Does it represent the top or the base of the pond? Okay, now in this case it's the top area is going to be maintained. So if I press OK, we should see that the top area stays the same and it's the base area that is reduced. Okay, now if we press OK now, what we see is we've now got this little dotted line. So this is the base and this is the perimeter around the outside here. So next I want to start designing the size of that pond. It's got the right slopes, but is it the right size? So we go back into the pond itself. Actually, there's one thing we're going to need in a second. I'll show you why. I'm just going to cancel this. And instead, can we go to Results and Inflow Summary? We've used this previously. Okay, so I'm in the inflow summary and I'm looking at the area and the area to be analysed. They're the same. Now this doesn't make sense because I talked at the start of this session about changing the pimp value to 60. So I was expecting the area to be analysed to be just 60% of the area. So something's gone wrong. I think I know what it is. So let us go back to the build and the tables, and we can see here that the preliminary percentage impervious was set to 60. However, this is, I don't know why this is needed, but we have two different places where we can specify this pimp value. This preliminary percentage is when we do the pipe design, but then when we come to do storage design, there is a separate place for that, and that is the percentage impervious column. So we also need to change that. So we've got that column switched on now. Under inflows, under the tables, and then if we can have a look at it, where is it? That one is still set to 100. So I need to change that one to 60 as well. If it was me designing the software, I would only have one place for that, but there are two places. So set that to 60, press equals, and those also change to a value of 60. OK to save it. Now let's go back under the results and look at the inflow summary, and what we should see, that makes better sense. So we've got the area of each inflow polygon, but the actual area that's going to be used by the rainfall landing on that area providing a contribution, is 60% of that. So if we added up all the polygon areas, it would come to 4.2 hectares, but the area to be analysed, in other words the area that actually provides runoff, is 2.52 hectares, and you should remember that value, 2.52 hectares. Okay, so we're going to design the pond to serve this area, this 2.52 hectares. Okay, so back into the pond and back into the sizing calculator, and this time we're going to go for quick storage estimate. Okay, we're going to be designing up into the, rather than the exceedance level of 32.309, we want to design up to the freeboard level. In other words, we want to keep all the water in the pond such that it doesn't exceed 32.109. Now we could at this point type in a volume if we wanted to, but we're going to calculate a volume. And we're going to go for the user input. The area is that 2.52 hectares that we calculated just now. And what we're saying is, of all the rainfall that lands on that area, we're going to assume that 75% of that runs off into the sewers and eventually through our pond and out to the outfall. So that's what we're going to have to contain. The discharge rate, as mentioned that earlier, that's 16.1 litres a second. In the UK, we derived that number by doing a greenfield analysis and working on the theory that we should have no detriment, we shouldn't make anything worse. But wherever that number comes from, you'd need to type it in at that point. If we have infiltration out of our pond into the surrounding soil, we will put it in at this point. We're going to assume not. We're going to assume either that there's some sort of lining on the pond so that it doesn't infiltrate, or perhaps we're in a very clay soil where we wouldn't get infiltration anyway. This safety factor is set to 2. That influences the infiltration rate. So if we typed in a value for infiltration rate, it would in this case divide it by 2. So no infiltration, this is irrelevant at this time. Quick analysis is fine. We don't need to see the graphs or anything like that. And we're going to use the 18 storms, if you remember, from the seasonal return period wizard. So this is 30-year storms, summer and winter, 9 different durations that we're going to analyze. Okay, and press OK to that. Sorry, not OK. Don't press OK. Press calculate. And we should see that the estimate has come out to be somewhere between 705 and 997 meters cubed. So this is just a kind of ballpark estimate. There's a lot of things that we don't know at the moment. We don't know exactly the configuration of the pond, if there's any infiltration, that will come along later. So this is really just a ballpark estimate. Okay. Now if we press OK at this point, what the software then does is it picks the middle of those two values. So 850 is our best ballpark estimate of how much volume this pond needs to be. We'll only know that for sure once we've done a full simulation, but that's a pretty good guess for now. Okay, and press OK on that. It would have changed the size of this pond a little bit. You can see, I think it's a bit bigger than it was before, and we can really see that when we press OK. Watch the size of this digitized area. So you can see it's now got a lot bigger. So this is really great because this gives us a really good visual on how big the pond's going to be, how much area it's going to occupy. So we see we've got the perimeter of the pond around the outside. The base of the pond is the dotted line around the middle. We've still got the blue line, which is the background from that CAD information that we digitized originally. So I probably want to switch that off now. That's not relevant anymore. It just gave us an initial shape and size of the pond. Now, depending on which version of InfoDrainage you're using, there is one final task that we have to do associated with ponds. So using the select tool, double click to go back into the pond properties and click on the advanced tab. And here we need to apply a Manning's roughness. So typical Manning's value for a sort of grassy filled pond is going to be something like 0.03. So apply that and press OK. So I've got my initial pond design. What I now need to do is to connect it up so that it connects to the pipe coming in from here and the pipe going out from there. So I'm going to do the inlet first. So it's going to be one of these connections from the tree view, and we can have anything we like. Pipe is probably the most common. At this point I was just going to introduce these no delay connections. Now these are useful when you're doing a sort of initial outline design. They're probably the quickest way of connecting things up. So if I was doing this as a real project, I would probably put a pipe in here. I would concentrate on getting the upstream and the downstream invert level correct. It would enter the pond just past the perimeter. But to be honest, we've dealt with pipes. We know how to design pipes, how to specify pipes. So I'm just going to use what I think is probably the quickest and easiest thing, which is a no delay connection. So I drag that no delay to the manhole that's immediately upstream of the pond, and then the convention is that you put it somewhere within the pond boundary. In fact, it has to go within the perimeter to make that connection. So put it somewhere inside the perimeter and click, and it creates this no delay connection. Okay, and as I said, good practice, always go back to the select tool to so you don't create multiple things. So the water is going to come out of this manhole and it's just going to arrive in this pond. So one thing that's useful is there should be some sort of structure that discharges from here to here. In this case, I'm going to go with an orifice. So find manhole S15, double click on it to bring up its properties, and what we should then see is on the outlet from this manhole, we've already got an orifice. That's the one that's created by default, but it doesn't have a diameter yet. So let's go for a 600 millimeter or 0.6 meter diameter. The invert level is fine. That's the downstream invert level of the pipe that's connected to it. So that all looks good. And then press OK. So like I said, whether you create one of these quick no delay connections or whether you put in a pipe and concentrate on its characteristics, its diameter, upstream and downstream invert level, you just want a connection, the connection which would occur in reality to take the water from this manhole into the pond. Okay, so that should be the pipe in, and to check that, if we double click on the pond itself, bring up its properties and look at the inlets, we should see that there's just one inlet coming into the pond from manhole S15, what we call a point inflow. Okay. So we've done the inlet. Let's go to the outlet. And again, I'm going to use one of these no delay connections. Perhaps if you were doing a more detailed study, you would use a pipe, specify its parameters, but I just want any old connection. So I'm going to go from the pond to the manhole. Now at this time, we get this this thing that you hover over and it says, depending on exactly where you put your cursor, it'll say either no, new or inlet. I'm going to explain more about that later, but for now we just want to go with inlet. So as you hover over it, rather than, if it says new, move it just slightly to the right and it should change to inlet, and then press OK. Okay, again, immediately back to the select tool. Okay, now let's go in and look at the characteristics. You can see by default it's specified an orifice. Let's go and look at the characteristics of that orifice. Now this time it is more important to get these characteristics correct, because this is what's going to provide the limit of discharge from the pond. And you remember that we were aiming for 16.1 litres a second, because that's our limit of discharge from the system. So let's figure out how we need to design that. Just going to come back to the PowerPoint a second to remind ourselves what we're trying to do. So Okay, so here's our pond. We've got our cover level, we've got our top water level, we've got our base level. So the depth of the pond is 1.675 meters. It shouldn't get any deeper than that. So what's going to happen is the pond's going to fill up during these severe rainfall events. As it does that, the discharge through the orifice is going to increase, and what we want to make sure is that when it gets to its deepest, its 1.675 meter depth, we don't exceed the 16.1 litres per second discharge. So that's our design criteria. Okay, so if we now go into the calculator, the design depth is 1.675 meters and the design flow is 16.1 litres a second. We've got this coefficient of discharge, fairly standard for an orifice, but it's going to give us a diameter of 0.077, 77 millimeters. And you can judge for yourselves whether that's realistic. If it's too small, if you think it's liable to blockage, then you have to think about whether you protect it, do some sort of cage around it so it doesn't get blocked, or maybe we need to switch to another type of control device, perhaps a hydro brake or something like that. But for this exercise, we're going to assume that we can use an orifice, so that's okay. Just one point of note, we can see it's 0.077 here. When I press OK, it appears in the diameter here as 0.08. We probably need to improve that. We need to present the 3 decimal places on this particular item, but be aware that behind the scenes it is using 77 millimeters, not 80 millimeters. Okay. So that's it. We've connected up our pond, and at this stage it's useful to do a check to make sure that it has connected up correctly. So for those of you who've done all the exercises, you remember flow paths is the way to check connectivity. So from the tree view, right click on the flow paths and add. Just do it again. Once we pressed add, you should be able to hover over a manhole. It could be any manhole upstream of the pond, but let's go right from the top. And then as you go down, you should be able to select any of these manholes. But if we go right to the outfall, crucially, you're looking for the square to turn green. And then when you click on it, you should get a red all the way through, which is great. And then right click on your flow path and show a profile. And then we can see how it drains down all these pipes. Something odd happening here. In reality, we'll probably go and check that, see what's happening and resolve that. But we can see it drains down to this pond here, and we've got the orifice and the no delay connection coming in, and then the orifice and the no delay connection going out to the pipes downstream. Okay, so we can have confidence that we've connected it up. This is shown as vertically sided. Perhaps it should really show it as 1 in 4 side slope, but we haven't got that level of complexity yet in the software. Okay, so we're all connected up correctly, but one more thing I want to do before we move to simulation is I want to put an overflow on this pond. So it's designed such that it should fill up to the top water level during a 1 in 30 year storm. But what happens if it was hit by say a 1 in 100 year storm? We don't want it to cause flooding in the area, so it's common practice to put some sort of emergency overflow on a pond where it's going to spill somewhere else. So let's do that now. If you're following the notes, we're starting a new section looking at overflow design, point 3 of the exercise 6. So what we do is we want to put somewhere that it's going to discharge to. So under your junctions from the toolbox, just take a simple junction. So we're just saying we just want a point outside of our network. Once it reaches this point, it's assumed to be gone from the system. We don't care about it from there. You know, in reality, we might connect this up to something, connect it up to the local watercourse, but we're just saying, right, once it's there, that's it. That's the end of our sort of responsibilities for it. We're just going to let it spill there. Okay. What I now want to do is I want to connect up a connection. And again, I'm going to use this very simple no delay connection. So drag it across, put it somewhere inside the pond. And I think I've mentioned this a few times, but by convention, we always go upstream to downstream. So we start inside the pond and come out and connect into this simple junction. So this is really just an end point. There's no physical structure here. It's just this orifice is going to discharge out of the pond. Okay. As with everything, go immediately back to the select tool. Now, I don't want an orifice here. I want a weir instead. I want it to weir over and come out of the pond. So double click on what is currently an orifice. And you'll see that there's two ways out of this pond, either through this orifice which we designed a second ago, or currently we're looking at this second orifice which has a diameter of 0. I'm going to swap from an orifice to a weir. Now the crest level of the weir is going to be the top water level, 32.109. And the width, I'm not that bothered about the width. I just want to make it very big so that during these really severe storms it's plenty big enough to spill out of our pond. So I'm going to make it 3 meters. Okay, so I press OK. And it should now look like this. So pipe coming in, orifice going out, weir overflowing. Okay, and the exact locations of these doesn't matter as long as it's somewhere within the boundary, within the perimeter of the pond. It doesn't change the hydraulic calculations at all. This is a good point to save our model, so just press save. And we're ready to conduct our analysis. So at this point we go into the analysis, check our analysis criteria. So we should see those 18 storms from the seasonal return period wizard. The output interval, this time I'm going to go with a shorter output interval. Remember, this doesn't change how the calculations are conducted. It just changes how often they're presented, either in the graphs or in the tables. So I'm going to present a result every 2 minutes. This time step, I talked about this in previous sections, but what we're looking for here is that we're looking for the model to be stable, to give us results that we can believe in. We check that by looking at the graphs, and I did talk about this earlier, but very simply, when you look at the graphs, you're looking for realistic flows, flows that increase during the storms, decrease afterwards. You can sometimes get negative flows as waters maybe flows backwards up the system. That's something that just could happen in reality. But what you're not expecting is sort of violent oscillations as flow rates change rapidly backwards and forwards. So if you see something like that, it's a sure sign of instability. And what we're trying to do is balance getting those stable results with the simulation time. And it has to be said that orifices, whoops, I shouldn't have moved the pond. I'll move it back by hitting the back tool. I was meant to move that dialog box. Need to change that back to 2. So what I was saying is it's a balance between getting accurate results and just how long you have to wait for those results to appear. In this case, with a pond and with some orifices and weirs, there's quite a lot going on. There's some more complex hydraulic calculations. So at this point, I'm going to switch to go to the shortest possible time step. It does mean that my simulations are going to take longer, but it does also give me the best chance that the model's going to be stable. So I've got everything set up here, and I'm going to press OK. Now back to the analysis and press validate. Should have no errors. If you do have any errors, then they will be listed here. You would double click on them and it would take you to the relevant place. Perhaps you haven't specified the width of the weir or something like that. Perhaps I don't know what else it could be. You haven't specified a diameter for the orifice that came in here, but there'll be some sort of problem with the dimensions. Hopefully not. Press OK. I always do one final save before I run a simulation, but press save. And now hit the go button to start the simulation. I will pause the video at this point to foreshorten it. It takes a minute or two, which is too long to sit and watch it simulate. Okay, so when the simulation is finished, we should be looking at a table like this, which automatically appears, and we are simply looking at one storm, the 15-minute summer storm for the 30-year event, and we can see that during that storm there was 59% of the pond still available, so currently very oversized for this particular event. However, that doesn't tell the full story. What you need to do is click on the critical storm. It's also useful, so that tells us that the 480-minute winter storm was the worst. Sometimes useful just to click on all storms like this to see them all, and then the critical one is listed, so still the 480-minute winter storm. Just 7% of the capacity available there, so our initial storage estimate, our quick storage estimate, was pretty good. The pond is slightly bigger than it needs to be, but a very good first estimate of how big this pond should be. So close this table, and at this stage we're going to save that again. Okay, so my pond's, I think, 7% too big. So what do we do about it? What process do we go through? Now, obviously, if there was flooding or discharge over that weir, then the pond would be too small and we'd have to make it bigger. But in this case, it's too big and we have to make it smaller. So what you do is you go to the results, and if necessary, open up that table that we were just looking at. Now, the crucial thing to look at here is that the maximum resident volume in the pond was 792 meters cubed. Now that provides a very good estimate of the size that's needed. It may not be quite the estimate, because we can also see that the maximum depth in the pond was 1.6 meters and the maximum outflow was 15.4. So we've got less than the depth that we're allowed, and therefore less than the 16.1 maximum discharge. So if we make the pond deeper, more of it is going to discharge, and therefore the volume may not need to be as big. So it is a bit of a sort of balancing act, but this value, this maximum resident volume, does provide a pretty good guess of your next sort of quick storage estimate, your next guess for how big the pond should be. And that's the one I'm going to use in this case. Okay, so close the table, double click on the pond, open its properties, go back into the sizing calculator, and rather than quick storage estimate this time, we're going to go for runoff reduction volume, I believe. No, sorry. No, all we need to do is to type in our guess there. So you remember it was 792 meters cubed of resident volume. I'm going to guess 795, very close to that. Press OK. And we should, as we press OK here, we should see the pond just get a little bit smaller. See, just a little bit smaller. So at this stage, save the model. You might want to, under analysis, you might want to revalidate it. Should be okay. Surely we haven't messed anything up too bad since we're only changing the size. Press OK, and now we're going to reanalyze it. So again, I'm going to press go and then pause the video until it's finished. Here we go. Okay, so our second simulation is now finished, and we do the same thing. Look at the critical storm. We can switch on all storms if we like. It's not going to change the critical one. It's still the 480-minute winter, but this time we have just 1% of the storage in the pond available. So this pond is now completely optimized. It's a lovely design. It very nearly fills, but not quite. So it's not too big, not too small. We've got a maximum upstream depth of 1.66 meters. We're allowed 1.675, so we're very, very close to that. We are very close to, but not exceeding, our 16.1 liters a second discharge. So we have now completely optimized this pond. It's as good as it's going to get, really. And that's the end of exercise 6.